functions as a service are deployable functions that run without an addressable server. Functions as a service scale without any work by the developer. When you deploy a function as a service to a cloud provider, the cloud provider will take care of running that function whenever it is called. You don't have to worry about spinning up a new machine and monitoring that machine and spinning the machine down once it becomes idle. You just tell the cloud provider that you want to run a function, and the cloud provider executes it and returns the result. Functions as a service can be more cost-effective than running virtual machines or containerized infrastructure because you're letting the cloud provider decide where to schedule your function, and you're giving the cloud provider flexibility on when to schedule the function. The developer experience for deploying a serverless function can feel mysterious. You send a blob of code into the cloud. Later on, you send a request to call that code in the cloud. The result of that execution of that code gets sent back down to you. What is happening in between? Why am I able to execute this code despite not deploying it to a server? Rodric Rabbah is the principal researcher and technical lead in serverless computing at IBM. He helped design OpenWhisk, the open source functions as a service platform that IBM has deployed and operationalized as IBM Cloud Functions. Rodric joins the show to explain how to build a platform for functions as a service, otherwise known as serverless functions. When a user deploys a function to OpenWhisk, that function gets stored in a database as a blob of text, waiting to be called. When the user makes a call to that function, OpenWhisk takes it out of the database and queues the function in Kafka, and eventually that function gets scheduled onto a container for execution. Once the function has executed, OpenWhisk stores the result in a database and sends that result to the user. When you execute a function, the time spent scheduling that function as a service and loading it onto a container is known as the cold start problem. The steps of executing a serverless function take time, but the resource savings are significant. Your code is just stored as a blob of text in a database, rather than sitting in memory on a server waiting to execute. In his research for building OpenWhisk, Rodric wrote about some of the trade-offs for users who build applications with serverless functions, and those trade-offs exist along what Rodric calls the serverless trilemma. In today's episode, we discuss why people are using functions as a service. We discuss the architecture of OpenWhisk, and we talk about the unsolved challenges of building a serverless platform. Full disclosure, IBM is a sponsor of Software Engineering Daily. If you have your finger on the pulse today, you're interested in blockchain and Ethereum. And the landscape is constantly changing, so there's a lot to keep up with. Subscribing to the Consensus weekly newsletter provides you with the most trusted source of information and updates on the blockchain space at softwareengineeringdaily.com/consensus. Consensus is the largest blockchain company focused on building software on the Ethereum platform. Consensus has built several of the leading dApps, decentralized applications, in the Ethereum ecosystem, and it offers some of the most popular free Ethereum developer tools such as MetaMask, Infura, and Truffle. These tools are essential if you're thinking about building an Ethereum dApp. To learn more about Consensus and Ethereum, visit softwareengineeringdaily.com/consensus and sign up for the Consensus weekly email newsletter. And if you want to hear a show about one of the topics, send me a tweet at software_daily and tag Consensus with the topic that you would like to hear about. Rodric Rabbah is a principal researcher and technical lead in serverless computing with IBM Research. Rodric, welcome to Software Engineering Daily.
Thanks, Jeff. I'm excited to do this.
In previous episodes about serverless or functions as a service, we've talked about how the architecture of applications can change to take advantage of functions as a service. And you work at IBM, you work on OpenWhisk, which is an open source version of a serverless platform, so you're well versed in this topic. The application model that we've used for years involves not only functions, but also objects and state and databases. So we all want to take advantage of this new serverless idea where we can just have stateless computation that we deploy as a function to an opaque blob of compute in the cloud somewhere. And if people are unfamiliar with this, we've done lots of previous shows where you can get the basics on serverless. So I'm going to assume that the listeners have some level of understanding about serverless architecture and what serverless actually means. What are the application architectures that are evolving to take advantage of these functions as a service?
Yeah, that's a great question. So functions as a service, when it really came out and as it's evolved, has proliferated this myth that functions are stateless, where in fact they're not really stateless. And that's a fact of reality. When you write code today, when you're going to run it in the cloud, you're going to be interacting with APIs. You're going to get your I/O from somewhere as an external source. And that inherently implies some notion of state. You're setting up database connections. You're going to be reading objects from a database. You're going to be using other APIs to enrich the functions and the capability that you're computing over. And so even though platform providers say functions should be stateless, it's really a myth. And to do anything real, you end up as a developer having to involve a lot of stateful management within your function itself. And that creates added complexity so that while functions as a service has been attractive, it's putting the burden on a developer to manage a lot of the state, a number of the things that you alluded to. And where I see a frontier in serverless computing really being pushed forward, and this is not just unique to IBM, but I think in general for all the platform providers looking in this space at about the same time, is looking at the state management and how you manage state complexity for applications. Because to build interesting applications, you're going to not only have functions that have to interact with the outside world, but they have to persist some notion of state in terms of the computation as it evolves over time. And you see this for where serverless is used today in terms of CI/CD, which is continuous integration delivery. You see it in workflow orchestration. You see it in conversation services and chatbots. There's a number of these use cases where you might have applications that you can build out of functions as a service, but you need a little bit more. And where we're looking to take this from Apache OpenWhisk and also its hosted version, the IBM Cloud, called IBM Cloud Functions, is to deliver that next tier of value proposition with respect to state management.
Let's dive into that a little bit more. Why do people talk about state being hard to manage within serverless functions?
Sure. If you look at how typically you compute in a traditional classic model, right? If you harken back to the von Neumann classical model of computing, you don't just talk about the CPU, right? The classical model is there's a CPU and a memory. And a lot of what you do in programming is really about bringing data into the CPU, computing on it, and storing it back to memory. And that model, while it has been very simple, conceptually, and has enabled a lot of innovation in computing, serverless computing today talks about the compute resource and not about the memory. And so our first task is to basically expand the scope of serverless to say, you're not only dealing with the compute resource, you also have to deal with the memory resource. And in fact, I've started calling this a new kind of computer. It's the cloud computer. But if you look at it in that way, there's a resource for compute and a resource for memory. I don't think it takes a lot of imagination to look at the complexity people have had to face in terms of the programming models that have evolved, the way you write programs, the way you optimize programs in the classical sense, that now has to be transplanted and applied in this new cloud computer model. And, in the imperative sense, you have constraints about, or you have concerns about how you have to manage the memory. When do you bring in the data from the memory to the processor to compute on it? How long do you keep it near the processor so that you have optimized performance? Because you don't want to fetch things from memory always, because that's an expensive operation. And that's why memory architectures have developed with caching layers, for example. But a lot of that complexity in a traditional architecture is mostly taken care for you. Whether it's the programming language, the runtime, the architecture is doing a lot of that for you. Transplant that to the serverless model or the cloud computer, You don't have that. We're building the stack from the bottom up, and we're building essentially with serverless functions as service just to compute management. So that means a lot of complexity falls on you. So where's your data? You have to now manage that yourself. How long do you keep your database connections open? You have to manage that yourself. Are you co-locating your compute and your data? You have to manage that yourself. I think that gives you an idea of the kind of complexity that, in a cloud native environment you're facing, and why you have to shift the burden to the provider, or sort of the provider of the platform itself, because these are going to be hard problems. And with cloud computing, you have less and less visibility just because of how nascent the field is in terms of being able to do deep performance analysis, deep analysis about where your hotspots are with respect to the platform. So you just don't even have the kind of visibility that you might when you're running code on your machine. So I think that's part of the complexity and part of the challenges that we're facing.
Okay, so when I talk to the previous people who I've had on the show to talk about serverless, the way that we frame the discussion is serverless is this thing where you've got companies who have giant data centers, and the way that they have been doing their cloud computing, they've been offering servers as a service. You can provision a server on demand, it spins up a server, and you've got a big blob of compute that you can do whatever you want with, and you address it like a server. And the idea of serverless is on these big cloud computing clusters, they have leftover space that people have not provisioned as addressable servers. So they can say, okay, well, we've got this leftover space, and we're just going to aggregate all of that together as this opaque blob of compute that is not durable, and we're just going to address functions to it and have those functions execute on that blob of compute. And because it is this shifting blob of compute with, variable SLAs, you're taking all kinds of different machines and just putting them together in this serverless blob of compute, and you're scheduling that blob of compute out as functions. Because of that, because it has, variable SLAs, you don't want to ascribe it any amount of durability. And that's why people say, okay, well, we don't really want to treat this as stateful, because to treat it as being stateful would be to say that this thing, if it fails, we're going to lose some component of state. But you're saying that the statefulness is actually going to be inevitable. We have to figure out how to imbibe that blob of compute with a sense of state. Am I encapsulating your arguments correctly?
Yeah, I think that's correct. So if I could comment on a couple of things. So, even when you run servers today, a lot of workloads tend to be idle for large portions of the time. So from a platform provider, you want to be able to reuse that capacity and actually use it for something else. So that's one aspect of serverless computing with functions. I can aggregate all of the excess capacity as a provider that I have in my data center, and now I make it available to others to run their workloads. So I shift some of the excess capacity and I can reuse it. So that's beneficial for me as a provider. But what it also does is it brings in this programming model, which is really rich, empowering in that it frees you from a developer's perspective of having to manage the servers in the first place. And now you can shift the operations burden from managing the servers to managing your code. It's not that there are no ops. You're trading one burden for another. But when you do this, and when you shift into this model, it's inherent in the kinds of applications that you're going to build that there is going to be some aspect of state. And if you don't take that into account and you don't make that first class, things that are attractive about this model will lose their value because it becomes expensive to, for example, reestablish database connections because your compute was ephemeral and you've lost it. If you're trying to use this model for doing things like machine learning or inference in that context, you might be loading very large, expensive models. And if every time your function resources are deallocated, you have to bring in those resources again from a database or wherever you're loading your model from, that's an expensive operation. You're going to want to optimize that somehow. Whose burden is that? Should that be your burden as a programmer? And then does the platform give you enough capability to be able to do that? Or does the platform itself have to inherently give you some of that capability that says, I'm aware of your state, I'm going to help you manage it because it's easier for me to do it. And just like I'm able to aggregate resources for compute as a service, I can do the same kinds of things with memory as a service. Now I can take advantage of locality in the data center. I can take advantage of knowing what state you're persisting, what state you're not persisting. And I think applications tend to be mostly stateless, but there is some aspect of the program that if you take it, you can partition it where state is localized to very small pieces. And because of that, then you can take advantage of that and optimize very specifically. And this is not really a new observation. If you look at the history of computing with stream programming models, high performance computing, a lot of this has been played over and over and over again. It's just not, now we have to transplant that context and apply it in serverless.
This episode of Software Engineering Daily is sponsored by Datadog. We know that monitoring can be a challenge. With so many services, apps, and containers to track, it's harder than ever to understand application performance and to troubleshoot issues. Built by engineers for engineers, Datadog is a platform that's specifically designed to provide full-stack observability for modern applications. Datadog helps dev and ops teams easily see across all their servers, containers, apps, and services to monitor performance and make data-driven decisions. To get a free t-shirt and start your free trial of Datadog today, visit softwareengineeringdaily.com/Datadog to get started. Datadog integrates seamlessly to gather metrics and events from more than 200 technologies, including AWS, Chef, Docker, and Redis. With built-in dashboards, algorithmic alerts, and end-to-end request tracing, Datadog helps teams monitor every layer of their stack in one place. But don't take our word for it. Start a free trial today, and Datadog will send you a free t-shirt. Visit softwareengineeringdaily.com/Datadog to get started. I want to jump ahead to talking about OpenWhisk because we've done a bunch of shows about serverless computing, but we've not done shows about how to actually build a serverless platform. You just gave a great motivation for why companies that have a large data center with excess capacity would want to have a serverless component of their data center where, the amount of resources that are in that serverless cluster are going up and down and external users are accessing that, or maybe even internal users, members of the company who want to use resources opportunistically. Maybe they've got some batch jobs that they want to run whenever there's enough compute, and a serverless platform would give them granularity for running that. And I think that's one of the motivations for OpenWhisk. That's one of the motivations for having an open source platform for anybody to deploy their own serverless system. So that's what OpenWhisk is. It's a server side of a serverless platform. So I want to get into talking about that. So let's say I define an action. An OpenWhisk action is essentially a serverless function. And if I would just want this OpenWhisk action to just simply emit hello world. I write it as a small JavaScript application. I invoke it using OpenWhisk. If we were talking about other serverless platforms, I would have very little idea about what would occur behind the scenes. I would just deploy this code and it would execute and then I would get a response. But since OpenWhisk is open source, you can tell me. So describe what happens end to end when I deploy that hello world JavaScript application on OpenWhisk and execute it.
Sure, that's a great point. And part of the open and OpenWhisk is that it's basically open source. It's free for you to use and deploy on your own, modify, etc. And I think that's part of an important platform because I'll answer your question in a second, but I wanted to make one additional point. Because we think this is early days for serverless and functions as a service, having an open ecosystem where we can push the frontier for this model of computing is also important. And as you pointed out, because it's open, you can go and inspect the guts and see exactly what's happening. And from the time you create the action, basically you start typically by developing the function on your browser or on your local file system using your favorite IDE. And then you make an API call to OpenWhisk or the hosted version of it, like in the IBM Cloud Functions, for example, that makes a copy of your function that then gets hosted on the server side. So this is the OpenWhisk side of things. And that function is there. There's no resources provisioned just because you created the function. It's only at the time when you actually invoke the function that then something happens. And that something essentially translates to the system having to, at the end, provision a container to inject your code into it and then send it any parameters, run the function inside that container, get the parameters out, and also get the logs out. So what happens in that flow is that there's essentially an API controller, which accepts all API requests, whether it's traditional create or delete operations or what we call activations. That's our terminology for running an action or invoking it. When the controller receives a request that says invoke an action, it posts internally a message over a message bus. And in the current implementation, we use Kafka for that, which is proven for durability and also low latency of communicating messages across a control plane. So the controller posts a request to the message bus that says, I have a request. Somebody would like to execute this function. That message is picked up by one of invoker machines, which are slaves in the system that understand how to talk to containers and receive requests, essentially try to dequeue them as fast as possible, provision a resource, and run them. So the flow is basically controller receives the message. It goes through a load balancer to the message bus, which essentially queues the message for a particular invoker to run the action. Eventually, the invoker picks it up, runs it inside of a container, and then gets the results, creates the activation record, etc. And you can see this if you run OpenWhisk locally. You can see it in the logs. We have very detailed logs which help you flow through the entire execution. You can also use that to measure how long you're spending in any individual step. And you can also observe that yourself if you're trying to use OpenWhisk for running other kinds of actions, which maybe we'll get into a little bit later, with respect to compositions. So not just individual actions, but compositions of actions together. There's slightly different behavior that happens in that context, which the system has to take care of. But again, because the implementation is open, you can take a look and exactly see what happens in that context as well.
Yeah, I do want to talk about the composition a little bit later, but about how OpenWhisk works, as you just described it, let's go through it a little more slowly. This architecture was described quite clearly in an article called Uncovering the Magic About Serverless, and I'll put that in the show notes, by a guy named Marcus Tomes. He describes it quite clearly as some diagrams. I found this really useful. So my function, I developed this function, and I'm going to deploy it to a serverless cluster. It's just a hello world function. And the first step is it hits Nginx, which is a reverse proxy and load balancer. And then it hits the controller. And the controller is written in Scala. It's going to do some orchestration between different components of this serverless framework. Describe what the controller does.
So the controller has largely two pieces. One is handling all the API requests, and the other is a load balancer, which is going to make a decision about where to run particular activations. And let me explain that in a little bit later. For the first aspect, which is just handling API requests, for CRUD operations, which are create, read, update, delete of actions or other kinds of assets that OpenWhisk support, including packages, triggers, and rules, it interfaces to the database so that it's creating its records for the functions that you want to run, or the metadata that says, I have an event. When that event happens, create a trigger and a rule that causes an action to run. The second aspect is the load balancer, which is given a request to run a particular action, which might come in by directly trying to invoke an action, or because you receive a trigger that says, when this trigger happens, execute the following action. It has to make a decision about where to run this particular action. And the reason there's a load balancer in the controller is because we are very sensitive to latency. And because spinning up a container for us to run the action in downstream is expensive. I mean, it can take somewhere from 500 milliseconds or even a second or more. You want to be able to take advantage of resources you've already allocated to run that particular function for that particular user. So if I have a container that I've provisioned in the past, the load balancer is aware of that and wants to route that request to that same container. So the controller is doing both aspects. It's handling all the API requests, and it's also trying to do the load balancing, which is a way of maximizing utilization in the system and improving the locality of where we run individual actions.
Mm-hmm. This is what other serverless platforms might call an API gateway or an API gateway, basically. It scales up and down depending on how many people are requesting actions from the serverless platform.
So the API itself, or the controller itself, is a finite entity in terms of its maximum capacity it can handle. If the controller if the system, detects that the controller would need excess capacity, then that has to provision itself, a next controller, or typically you might deploy many controllers behind the same Nginx and then have some load balancing that Nginx is doing for you. It'd be an interesting proposition to say, can you implement the controller itself as essentially a serverless system, because you want that kind of elasticity you alluded to. It's because the controller in a typical deployment would be heavily used and essentially up all the time servicing requests. You essentially cross over the point where it makes sense to run something as a function as a service versus a dedicated resource. So when we deploy the controller as part of OpenWhisk and even IBM Cloud Functions, we actually deploy it as a container, and it's managed as a single monolithic microservice.
Yeah, and then so the next step is the controller takes the function and hands it off to CouchDB. So, if I pass my Hello World application, if I send a request with my Hello World application to OpenWhisk, the controller is going to hand that to CouchDB. The entire function gets stored. I guess this was something that was kind of like surprising to me, but it's just like you just store the function in a database, and then when somebody calls it, you take it out of the database and you're eventually going to load it into a Docker container. So why CouchDB? CouchDB is this system of record that stores all of the functions that people are going to invoke against OpenWhisk. Why do you use CouchDB?
Right. So, and some of this is historical in that when we started OpenWhisk, we weren't quite sure how the eventual schema was going to end up. And one of the advantages of NoSQL is that you don't have to, CouchDB is an example of a NoSQL database, so you don't have to lock into a particular kind of schema. And then as we were evolving the implementation very rapidly, it sort of freed us from having to manage a large aspect of that and worry about schema migrations and things of that sort. So it fit in that model. It also allowed us to have indexing functions that we can push against the database. So we co-locate the system of records and the actions themselves with map and reduce functions that we wanted to apply against those functions to compute various kinds of indices. So the kind of metadata that we typically store inside of CouchDB is small enough, and we wanted additional flexibility with respect to the schema to where it fits. Now, you can argue for other metadata, like the triggers and rules, which are really relational by definition, that we should have used a different data store for that. And I think that's something that's within the interest of the community, where we'd like to be able to plug in different databases that we use for different entity management. And the nice thing is that because OpenWhisk is part of, code is on GitHub, we've had people ask these kinds of questions. Can I plug in my own database? And we had factored the interfaces so that you would be able to bring in your own implementation of a database and use it or swap one out for the other. Now, the details matter, and it might not be as easy as I make it sound. But initially it made sense to use NoSQL database plus an object store ultimately for storing the large code blobs. And the way I look at it really is you want a mirror of your local file system in the cloud. So whether you use Couch or S3 or object store, that's really what you're trying to do. I want to mirror my local development environment in the cloud, the way I organize the files, the way I organize my projects, etc. And then when you want to run, I want to be able to figure out what you're going to run and then bring it into the resources I've provisioned to run that code. So, CouchDB is an implementation detail. It has some advantages for us today, but it's also a very interesting question about now that OpenWhisk has matured, and in terms of our operational experience of running OpenWhisk in the IBM cloud, starting over from scratch, might we choose different strategies and might we use different data stores? I think that's a valid question. It makes sense for different kinds of entities that we manage.
So after I've gotten my function stored in CouchDB, that means that whenever I want to call that function, whenever I want to call my Hello World function, I can again just ping the OpenWhisk platform, and my request is going to get load balanced across one of these controllers, and it's going to fetch that function from the database because I stored it there earlier, and it's going to schedule it on this fleet of Docker containers that are called invokers. And before it gets scheduled onto those Docker containers, it gets queued up in Kafka. Why do you need this buffer, this Kafka buffer, for scheduling functions? against this fleet of invokers?
Sure. The main reason is reliability. You're in a distributed system. Networks can partition, system components might fail, and you want to essentially try to provide a notion of some reliability to the end users. So once we've accepted a request, we try to move it into basically a more persistent data store or medium, and we use Kafka for that. So we defer all the reliability to Kafka. And now once the request is in Kafka, if the controller goes down and comes back at some point in the future, or if all of the invokers in the system go down and then come back in the future, they can pick up from where they started. So it's providing a notion of reliability. And communication in distributed system is not zero latency. You need some mechanism for queuing, especially as load increases. Sometimes you might not have enough capacity in the system. What do? You have to be able to handle back pressure somewhere while you either try to provision new resources or wait for capacity to be available. So Kafka gives us not only the reliability then, but also the queuing aspect to handle more load where we might not have enough capacity in the system. This you might be indirectly touching on an interesting property of serverless, which is service level agreements. Typically, when you talk about service level agreements, you say my uptime is 99.9% of the time. I have 3 nines or 4 nines or 5 nines. But in serverless, I think that's not as meaningful. And it's a little bit more challenging to come up with an SLA for serverless. I think the kind of guarantee you want is how much or what percentage of the time are you going to process my requests within, say, 1 millisecond, right? Because if our uptime is 100%, but we queue your request for minutes at a time for a function that might execute for 100 milliseconds, that's not an interesting SLA. Rather, we want to say, with 4 nines, we can start executing your function within 1 millisecond. Now, that's the kind of property that I think you need to build interesting applications, especially when you might be latency sensitive.
All right, so after my function gets buffered up in Kafka, eventually it's going to get scheduled against this fleet of invokers, these Docker containers. Is there anything special going on at the layer of invokers? Like what's going on there? Do you use a scheduler like Kubernetes or Mesos, or did you write your own scheduler?
Right. So we wrote our own scheduler, and the reason for that is latency again. If you try to look at what's happening in the invoker when it receives a request, we wrote our own container pool management because we needed to be able to take advantage of locality. And we also wanted to be able to provide sort of container resources with as little latency as possible. So typically, if you try to spin up a new container for every function that you're going to run, as I alluded to earlier, a Docker run can take anywhere from 500 milliseconds and up. And under load, that time goes up. I've seen times over a second for spinning up a new container. And for Kubernetes, I've seen some numbers that say they can spin up a pod in sub-second. But the latency for that is, I think in general doesn't work. So what we do is, what the invoker is doing is that it tries to create as few containers as possible for individual functions that it's seen in the past. And it wants to cache containers that it's used in the past and reuse them. And the way we do that is by pausing and unpausing containers. And if you think of the lifecycle management of a container, it goes through a Docker run. You run the function, and then there's a Docker pause immediately after your function has returned. So we do that because we don't want the functions to essentially continue executing. It has to do also with billing and metering. So once your container is paused, it's essentially not consuming resources. We can keep it around for a while. And if we get a new request to run that same function from the same user again, we can just unpause that container and then start executing again. And the Docker pause and unpause, we actually use something lower than Docker. We use runC. And the latency for doing that is on the order of 10 milliseconds, whereas a Docker run, let's say on average, is 500 milliseconds. So it's a very big performance gap. And this is also part of the reason why we don't use Kubernetes or Mesos or a container management system at that level. Because the way those systems are architected, I think today they're not quite there for being able to do that kind of low latency operations for functions as a service. That said, there's a lot of effort in this space and a lot of interest in being able to reuse some of these container orchestration systems for that purpose. So I would expect that in the future things will change. But until they do, we've had to sort of fill that gap, and that's part of why the Invoker essentially is a custom, bespoke container management system that we built as part of OpenWhisk.
Prime flips the typical model of job search and makes it easy to apply to multiple jobs and get multiple offers. Indeed Prime simplifies your job search and helps you land that ideal software engineering position from companies like Facebook or Uber or Dropbox. Candidates get immediate exposure to top companies with just one simple application to Indeed Prime. And the companies on Prime's exclusive platform message the candidates with salary and equity up front. Indeed Prime is 100% free for candidates. There are no strings attached. Sign up now and help support Software Engineering Daily by going to Indeed.com/SEDaily. That's Indeed.com/SEDaily if you're looking for a job and want a simpler job search experience. You can also put money in your pocket by referring your friends and colleagues. Refer a software engineer to the platform and get $200 when they get contacted by a company, and $2,000 when they accept a job through Prime. You can learn more about this at Indeed.com/prime/referral. That's Indeed.com/prime/referral for the Indeed referral program. Thanks to Indeed for being a continued sponsor of Software Engineering Daily. If I ever leave the podcasting world and need to find a job once again, Indeed Prime will be my first stop. Yeah, so one of the parts of serverless that is important to recognize is that when I request my function to be called, when I request my hello world function to be called, it has to get scheduled and deployed to a container. And this leads to what is called the cold start problem. And because you have to spend the time spinning up an actual container, contrast that with the pre-serverless world where you've got a container or a server that is already sitting there, and all you have to do is send an HTTP request to it, and you get a response, and it's low latency. This is like one of the trade-offs of the serverless world, is because the trade-off is you actually have to, you're going to have somebody spinning up this opaque blob of compute, and you have the cold start problem, and you're talking about, okay, we're going to have this cold start problem, but if somebody's going to call hello world one time, the cold start problem, okay, kind of unavoidable, we just have it. But if they're going to call hello world and then a minute later they're going to call it again, and then 3 seconds later they're going to call it again, and they're going to call it continuously for 3 hours, and then they're going to stop calling it, you would much rather spin up a container and keep that container up so that you can serve more hello world requests. So help me understand, to what degree does the user tune how much they want their container to stay around? Do I have to tell OpenWhisk, hey, I'm calling hello world and I'm going to call it again for the next 3 hours pretty frequently, so keep my container going? Or is OpenWhisk, does it intelligently figure out that it's going to be called frequently?
Right. So I think that's a great question. So OpenWhisk today, and the way it works, when you run the function, as you noted, we'll spin up a new container. Now, it behooves us to keep that container around for as long as possible in the pause state, because then when we need that resource again, we can just unpause it. The load balancer knows where that container is and tries to go to it. So we get some of the effect that way. Another aspect for the system in trying to mitigate this cold start latency is trying to keep what we call stem cell containers around for a bit. A stem cell container is essentially a container that is ready to run. We don't have to do a Docker run on it, which saves us 500 milliseconds or more, but doesn't have any user code initialized or specializing it. So you pay the cost of loading the user code into it, which can be expensive, but if you're loading a large zip file, for example, but in most cases is on the order of a few milliseconds. So that's another aspect of the capabilities of the system to try to mitigate code latencies. But that's largely where things stop today. And as an end user, we've seen, and we get this question a lot, how can I keep my container around? And how long will my container stay around? So there are tricks And they're largely just tricks or hacks that people do today to keep their containers around by constantly pinging them. So you can ping them by firing an alarm, which generates a trigger that then causes the action to run. The action says, oh, I'm just a warm-up trigger, do nothing. So that keeps the container alive in the system. But that's a silly way of doing it. One, it's putting undue burden on the programmer to do this. And two, now we're using resources to wake up a container that essentially does nothing. So it's the kind of capability that you want to shift to the platform that either tries to do predictive analysis or tries to give the user some capabilities that says, here's a distribution of my load, and try to use that to keep my containers around as much as possible. This is, I think, a complicated problem, and there's probably good queuing theory models to explore this a bit. In some ways, also goes back to my service level agreement kind of model. I might have finite resources, so I don't want to keep your resources around if you're not really using them. But if you're an important customer or you're very latency sensitive, say chatbot or conversation service, hey, a 3-second latency spin up a container is basically dead in the water. That kills the user experience. So there's work that has to happen in the platform to make the latency very low, to deliver that user experience that you would get with a dedicated resource. And I think that's part of the challenge and the next frontier in computing in this model. And all is not lost in that, at least with OpenWhisk, we have the notion of sequences, which are actions that are going to run in essentially a pipeline manner or producer-consumer manner. We can use that. We don't do this today, just to be clear, but we could use that as a way of predicting what actions you're going to run because we essentially have a history. When you start executing particular action, we know you're going to also execute these other actions. So we'll have to go ahead and provision resources to cut the latency, and that's a form of speculation that the platform could do. So I'd like to see a model where the platform is doing more of this rather than the end user doing this. But there's also a hybrid model, and history tells us the hybrid probably works well, where the user might hint at what their load looks like. And then the platform uses that in combination with its speculation techniques and its prediction techniques to mitigate the cold start latencies. Does that kind of answer the question or where you were trying to get at?
Yes, it does. And I want to talk about some of the other canonical problems with serverless, and especially some of the stuff that you've addressed in your research. We've been talking about how OpenWhisk as a specific serverless platform is architected. Now I'd like to talk about the usage of that kind of platform. And we've done a bunch of shows about event-driven architectures and how event-driven architecture relates to serverless applications because you have these events and one event triggers a serverless function, and then the serverless function might cause another event trigger. And so you get this cause and effect chain of different serverless functions being applied to one another, and that's how you start to develop rich functionality out of these fairly narrow functions as a service. It's almost like each function as a service can be the size of a helper method, and you have these helper method function as a services that you want to tie together to create rich functionality. And if I understand your literature correctly, this is what you call composition. You want to compose different serverless functions together to create richer functionality. Is that what composition is?
Yeah, absolutely. It's saying that functions are the building blocks, and applications are made up of many functions that have to communicate and orchestrate a data flow between them. And composition is essentially the mechanism and the programming approach that we've taken to enable this kind of model on top of functions as a service and serverless computing.
Mm-hmm. Now, in a monolithic application, I've deployed my giant application to a container or a server somewhere, and the upside of that is that all of these different methods are sitting in the same machine. So if I've got a method that if I hit an API endpoint and that API endpoint calls a method, which calls another method, which calls another method, it's not really a big deal. All of these methods are sitting on the same machine, so it's just a single machine. It's unlikely to have distributed systems style problems. But when we break those methods into their own functions, and you get these different functions and different helper methods that are sitting in different machines, this becomes a distributed systems problem. All of the latency issues that we articulated with the cold start problem, these become a real issue, because if you've got, like, if I need to call, one API endpoint that hits a helper function as a service that needs to have a cold start, which hits another function as a service that needs to have a cold start, which hits another function as a service that needs to have a cold start, this is going to compound the latency, which can be a real issue. Am I articulating one of the problems that you wanted to tackle with your studies of composition?
Absolutely. I mean, this is, goes back to, a lot of the points that you're right on with. And there's two things at play here. One is this programming model where you try to deconstruct your large monolithic application into functions and then describe your application as a composition of functions is in some ways good software engineering. But if you look at it from the context of parallel programming or distributed programming, it's kind of like the Holy Grail in that serverless is forcing you, by construction, you must decompose your application to small functions. But if you take that to the extreme, then you're going to pay very heavy costs with respect to performance, given where the systems are today. So you have to try to recoup some of the sort of monolithic style of the application, but without trying to compromise essentially the good software engineering principles that you might have applied by decomposing code into individual functions. Maybe you wrote different functions in different languages because it just suits the problem that you're trying to solve better. And so with Composer, which is something that we've released out of IBM Research as a technology preview, it works with OpenWhisk. We'd like to get users to use it to give us feedback and evaluate how we're doing in the space. But part of Composer is to try to recover this aspect of the monolith by saying the applications might be individual functions that are cloud functions or inline functions that you write in place. But we want it to come down to a representation of that composition in a way that then we can build tooling on top of it, like compilers that do optimizations on that composition. So an example that fits in the context of what we're talking about here is Fusion. I have a function that then talks to another function that then talks to another function. Rather than running them as three separate containers as part of OpenWhisk, we fuse them together into now a single larger function, and we run it in one single container. The advantage of that now is that you don't have the three cold starts. You might have only one. The communication between the functions now doesn't have to go through the system or the system of records. It can be very local. And this is an example not only of the state management you want to get at, but also the kind of compiler optimizations you might want because there's performance advantages to it. Informal experiments that we've measured, you can get 30x performance gains for even simple functions that you fuse in this way. And so the idea is really with Composer, is to expose the functions themselves as the individual building blocks, expose the communication between the functions, that's the data flow between them. And third is expose the state that individual functions might want to persist across activations. And with these three primitives sort of exposed as building blocks, then I imagine how we can build tooling on top of it to do compiler optimizations, to do automatic state management, to do runtime optimizations. And this is really the frontier that we're pushing from my group in IBM Research.
Can you give an example of when a developer would want to use Fusion?
So the idea is not necessarily for the developer to say, hey, I want to fuse these two functions together, but rather the developer says, I have two functions. I wrote them in a way that's natural to me. It's the system's job or the compiler's job to figure out when it should fuse them together. But given the state of things today, we've suggested to users, hey, for performance reasons, you should essentially apply manual fusion, which essentially takes all the functions and inlines them together into a single larger function. And you'd want to do this if you're building, for example, a chatbot where you're latency sensitive and the latency of the system might be too expensive for you to tolerate if you have too many cold starts for an infrequent use case. And this is a real use case where we've actually suggested to users, hey, I think for your sake here, you should just manually fuse all these functions together. So it typically happens that if you have functions that are written in the same language, like all Node.js code or all Python code, and you're really concerned about latency and performance, and your load is such that it's very infrequent to where you might suffer from a lot of code starts, you'll want to apply manual fusion. Our goal, however, is to say, really you shouldn't be optimizing things at that level manually. It should be part of the automatic tooling that the platform provides, that IBM Cloud Functions provides, for example, to do that optimization for you. And then we'd like to be able to broaden it so that you're not just restricted to fusing functions that are in the same language, but also how do you fuse languages across languages? Because I might have written an application in this model where I have some functions in Node.js, some functions in Python, some functions in Java. You typically can't do that very easily yourself. You have to increase the complexity of your code. So that's part of what we'd like to automate and mechanize and provide that as a platform capability rather than shift the burden to the end user.
There's a term you define called client-side scheduling. Can you explain what that means?
Sure. So client-side scheduling in the context of, so this came up in the context of exploring compositions. So let me give a simple example where you have a function that you want to execute conditionally if the result of some other function is true or false. Where do you do that orchestration that says, run the first function, look at its result. If it's true, then invoke the second function. And if it's false, then do nothing. There's a scheduler that you have to run somewhere, or you can think of it as a workflow executor. We've called it a scheduler because essentially it's scheduling the execution of your application. You can imagine that you would run this scheduler in a client like a browser. So you can write a Node.js application that runs in your browser that says, use the OpenWhisk API to invoke the first action, get the result, and in the Node.js code that you're running, say, in your browser, the JavaScript code that you're writing in your browser, you're doing the conditional checks and then explicitly doing the invokes of the functions. So by client side, we mean it's a composition that runs outside of the serverless system itself. So the composition itself is not a serverless function. It has to run somewhere else. But by doing that, you can free yourself from a lot of the limitations, rather, that the serverless platform imposes on you. Like the client scheduler might be a long-running orchestration that might last many tens of minutes. Typical function that runs in a serverless setting has to finish within 5 minutes and may not consume more memory than allowed. So if you want to break out of those limits, either you have to do something different within the platform itself, or you have to run outside of the serverless platform. So we call anything that you do to do this orchestration outside of the serverless platform as client-side scheduling. And it's a way of executing your composition, but using the API of a serverless framework, and then you logically doing all of the things that you have to do to keep navigating the execution.
You mentioned this project called Composer. Can you explain in a little more detail what Composer is?
Sure. So Composer is a library that we implemented currently in Node.js. It allows you to describe how you want to compose functions together and impart data flow and control flow. So in the example I gave earlier, where you want to do conditional execution of an action, you would express that in Composer with what we call a combinator. So you do, the name of the library, for example, is called Composer. You do composer.if, and that's a function call where you give it up to 3 parameters. The first is the condition expression or the cloud function you want to run. That's going to give you whether you're going to go down the then branch or the else branch. And then either a function or a cloud function or inline function that you would run for the then branch and then the else branch. And Composer essentially gives you a library of control flow constructs to do things like try-catch, to do an if-then-else, to do a loop, to do things like map and reduce or parallel and join kinds of compositions. And the reason we took this library-based approach is we didn't want to invent a new language, but we also didn't want to change the semantics of how you might write an if-then-else in an imperative style, say in JavaScript. In JavaScript, you just start writing if A, then B, else C. We needed to extract from that sort of the 3 things that I was alluding to before. Which functions you're going to run, what's the control flow, what's the state. And so by using this library of creating compositions, we force you into a style that helps us identify the control flow and the data flow and the state. And to make it easier for you to develop these compositions, we also built a tool called the shell, And what the shell allows you to do is visualize your composition as you're developing it. So you can write your code in your favorite editor, you point the shell to monitor that file, and as you're building out your compositions by using more and more combinators, you actually have a visual representation of your control flow as you go along. And that helps you in debugging your code, and you can sanity check that you've actually constructed an application that sort of fits you with your mental model and your block level diagram that you might have.
Great. So I read this paper that you wrote where you explored something called the serverless trilemma. And this was a way of presenting the trade-offs of a serverless application. I thought this was useful because it presents a framing that developers can start to look at and say, okay, well, these are the fundamental, it's almost like the time-space fundamental trade-off in regular computing. You have these three trade-offs where functions should be black boxes, function composition should obey a substitution principle with respect to synchronous invocation, and invocations should not be double billed. So there's going to be trade-offs between these three areas. So I want to go through these and define them and start to flesh out what your theories are behind the serverless trilemma. So first of all, the one corner of the triangle is that functions should be black boxes. What does that mean?
Right. So we believe that some of the fundamental value propositions in serverless is that you can write functions in just about any language that you choose. And because of that, it empowers you to use the right language for the particular problem that you're solving. If you're going to support more than one language, at some point, this polyglot functions, then you might want to look at the functions themselves as a black box. You can't look inside. You can't see what they're doing. You don't know what languages they're built in. And if you're going to treat them that way, then you also can't necessarily modify them. So that fits in the context of composition, because if you want to do something special in the context of composition to satisfy some of the other constraints, or you simply want to support the ability to compose functions that might be written in any one of these languages, you have to either buy into this notion that functions are black box. I don't know what they're doing. I cannot modify them. Or you have to say, I don't care about this property because I care about some other properties, which I guess we'll get into. And that's kind of a trade-off that you make. So strictly speaking, black box just means the serverless platform shall support functions written in any language or presented as just strictly as binaries. They're unmodifiable. I can't inspect them. I can't modify them.
Mm-hmm. You touch on the serverless substitution principle. What is the serverless substitution principle?
So by substitution, we mean that if you take two functions and you compose them together, we'd like the composition itself to be a function. It has to behave as a function. I have to be able to call it as a function. I should not be able to distinguish that I've called a composition from individual actions. And in OpenWhisk, we had an example of this even from very early days, because we thought this was a fundamental property even when we were building OpenWhisk with sequences. So when you use Apache OpenWhisk, today you can create individual actions or you can create sequences, which is a primitive composition that essentially forms a pipeline. The way you execute the sequence is the same way you execute the action. If you were to look at an activation record for a sequence versus the activation record of an individual action, they look the same. They both have a result, and they both have a start time and an end time. And moreover, I can take that sequence and now further compose it, say, with other sequences or other actions. So it goes to sort of this layered model of programming where you start with a building block, functions for us, and you want to build libraries out of them, and you want those libraries to further compose into applications, and essentially to continue increasing modularity and reuse. Everything should have the same shape. And in this context, everything should really look like a function. So substitution really goes to functions are the building blocks. Compositions of functions should also behave as functions. So I can always substitute a composition for a function or a function for a substitution.
All right. So the final corner of the triangle is the double billing issue. And you talk about how if there's a remote scheduler for your composition of functions, then you have a double billing problem because you're paying for the scheduler as well as the functions that your code is getting scheduled onto. So what is the double billing problem? Why is that important to this trade-off?
So the double billing applies really if you're going to try to run the composition inside the serverless framework. To the client-side scheduling that you asked about earlier, right? If I'm running the scheduler, essentially, that says compose function A with function B on my laptop, then I'm not necessarily subject to double billing in that the serverless platform is not billing me for that scheduler, right? It's running on my laptop. It's outside that system. But I have to keep my laptop on. Now, the composition that I have running in my laptop can't be reused, so other functions can't really call into my laptop to use it. So if you want to bring the scheduler into the serverless model, then now you're subject and you have to play by the rules the serverless model applies on you, which means that you can't run forever. Right? So typically actions will run for no more than 5 minutes. At that time, your resources are freed up whether you're done or not. So if you want to compose two functions that themselves each take 5 minutes, there's just no way for you to execute that code without running the scheduler at the same time as your other functions, and then having to possibly respawn yourself so that you can see if the execution has finished. And now what you've done is you've written code that is basically paying for the idle time or the waiting time of the scheduler in the serverless framework. So not only are you paying for the execution of the individual actions that you've run, but you've paid for the scheduler that you're running as a function in a serverless platform. And it's not just a paying in terms of cost, you're paying in terms of time, which means you have to be subject to this time limit that the system imposes on you. And you have to do some extra things to deal with corner cases where the things that you're composing run for more than 5 minutes. So we use the term double billing because I think it's easy to understand in the context of I'm running the orchestration as a function. I'm going to pay for that. I'm running the actions as a function. I'm going to pay for those. And so now I'm double billed because I paid for two things. And from serverless, right, one of the tenets of serverless is don't pay for idle time. And the scheduler's role is really to just sit there and wait between executions that say, is it finished? When it's finished, then I make a next decision about what to execute next and execute. So double billing really refers to the schedulers running inside the serverless framework and having to deal with either the time limits that the system imposes on you or the metering that it does in terms of the dollars you pay for the scheduler itself. So together, double billing, the black box, and the substitution principle provide three constraints that, as a provider of a serverless framework, you have to choose among or do something special to support all three.
Mm-hmm. Now let's bring this full circle. The serverless trilemma was this paper that you wrote about constraints that a serverless platform operator is going to need to abide by. We started this conversation talking about OpenWhisk, which is a serverless platform that you've contributed to heavily. Explain how the ideas that you explored in that paper, the serverless trilemma, how did those affect the development of OpenWhisk?
Yeah, so a lot of those ideas came out of our work with supporting sequences in Apache OpenWhisk. And as I alluded to, sequences and the way they evolved, we started running them so just to remind the audience, a sequence is essentially an action that runs, which was going to individually call actions A, B, and C, say, for a composition of those three actions. We started by having a version of sequences which itself ran as an action. And then we realized that while we were able to satisfy the substitution principle and the black box principle, we weren't satisfying the double billing. You were paying for the function, which was the sequence, and the individual actions. So as we tried to figure out how we best implement sequences in a way that also avoids double billing, as I alluded to, it's not just a cost, it's a time limit issue. We change the sequence implementation, essentially internalize it into the controller. And so while we were talking about the controller earlier, I left out that there's special schedulers within the controller that understand the kinds of actions that you're running. So a particular kind is the primitive action, a primitive function, but also a sequence. And so if you're running an execution that's a sequence or a composition that's a sequence, the controller understands that, and then it schedules it internally. And because of that, we're able to provide essentially a trilemma satisfying implementation of sequences. And that's why sequences in OpenWhisk today are not double billed. They're actually the most efficient way of running compositions if you just need a straight line code. They support the black box because you can compose functions that are polyglot and essentially solve the double billing and the substitution principle. So a lot of our thinking in this space really evolved by actually having to build something that provides a pleasant programming experience in this context and doing it in the context of OpenWhisk. Now, where we stop with sequences, where OpenWhisk stops with sequences today is you can't do control flow. I can't do an if then else, right? And sometimes you might want to do an event condition action. I want to short circuit the sequence. And I might want to do error handling. My sequence errored out. I want to try catch. I might want to flow parameters from one action at the head of the sequence all the way to the tail of the sequence, but without really having all the individual actions in between see that data, because it might be a secret that I want to manage. And I want to sort of keep a separation of secrets from the rest of the data flow. So when you start looking at going from the simple control and data path that sequences give you to building larger and more rich applications with different kinds of computational graphs, you need something new. And so this is where we started building Composer. And as we built Composer, we also worked on the user experience. And so Composer and the shell, I think, go hand in hand for that. It's available on NPM. You just go download it and use it. And as we were doing this for composition, we realized that then again, we have this trade-off between the three axes of the serverless trilemma to solve. And what we've done with Composer today is we've put out an implementation that supports black box composition. To some extent, we're working on addressing the double billing issue. And some of the changes that we're contributing from IBM Research back to Apache OpenWhisk will address the substitution principle as well. So just like we had done in sequences before, we'd like to bring this full capability of compositions that are trilemma satisfying to the framework. And this is what sets, I think, Apache OpenWhisk in our work with it from IBM in that context. We can make these changes. And one of the things our paper shows is that the platform has to do something special if you want to satisfy all three aspects. Otherwise, you have to break one of them. There's just no way around it. And if you look at some of the other models in the space, you can really cast and see which of the three constraints they break.
All right. Well, I'd love to wrap up by just talking a little bit about your research and what else you're concerned with around the serverless area, because I haven't seen many papers written about serverless other than the serverless trilemma and I think a few others. What are the areas of research around serverless that you would like to examine?
There's so many. And this is, I think, what's exciting and actually a good place for us from IBM Research to drive some of these. And, the framework to look at this, and I think the way to imagine how we're approaching this is you look at serverless as a new kind of cloud computer. Composer gives us essentially a foundational model for how we want to program this cloud computer. And now we have to build a stack of middleware, tooling, programming clients, et cetera, on top of it to make the user experience pleasant, to deliver runtime performance that's good, to keep presenting essentially various value propositions. And you can look at things that we're doing in the context of analyzing the functions themselves to know whether they're actually stateless or not, looking at compositions of stateless functions. Have you composed functions that are well-formed? Are schemas aligned properly? What are the issues around security in the context of compositions? Can you do things like taint analysis to say, hey, look, your composition is leaking sensitive data. You did not intend to do this, perhaps. Can you provide provable guarantees in this space that, hey, your composition is sound or not sound? Can you do things with respect to runtime optimizations? Because I have the composition, I know where you're going to go in the space of your computation. Can I use that to inform the framework about what resources to pre-provision and how to optimize your code for cold starts and warm starts? Can I do things like fusion? Can I do function reordering? So there's a lot of things that fall in the context of analysis, compiler optimizations, runtime optimizations, and tooling. And we're really looking at the full gamut of these and sort of taking a very vertical approach, from the bottom up in terms of trying to deliver a serverless computing programming model in this space that really tries to target sort of cloud native by construction with a lot of interesting value propositions.
Okay, Rodric. Well, it's been great talking to you. I am fascinated with OpenWhisk, and it's really been great to get a look inside of how a serverless platform actually works. Thanks for coming on the show.
Thank you, Jeff. This was great. I really enjoyed it.
Simplify continuous delivery with GoCD, the on-premise, open-source, continuous delivery tool by ThoughtWorks. With GoCD, you can easily model complex deployment workflows using pipelines and visualize them end-to-end with the value stream map. You get complete visibility into and control over your company's deployments. At gocd.org/sedaily, find out how to bring continuous delivery to your teams. Say goodbye to deployment panic and hello to consistent, predictable deliveries. Visit gocd.org/sedaily to learn more about GoCD. Commercial support and enterprise add-ons, including disaster recovery, are available. Thanks to GoCD for being a continued sponsor of Software Engineering Daily.
Wow!